Hello everyone. So in this part of lecture 6, we are going to learn how to find the electric field of an infinite cylinder. So let's get started. So let's imagine that we have an infinite solid cylinder like this with uniform charge density rho. Now let's say that this is the axis of the cylinder and this is the radius A. Now, as the charge density is uniform throughout the cylinder and it is infinite in length, then the electric field here should be directly outward from the surface of the cylinder. And as this is a solid cylinder, it will have electric field inside the cylinder as well, like this. Now, to find out the electric field due to this infinite solid cylinder, we have to consider the segment inside the cylinder and the segment outside the cylinder separately. Let us denote the segment inside the cylinder as segment 1 and the segment outside the cylinder as 2. Now, if we want to find out the electric field at any random point inside the cylinder, which we are calling segment 1, then the distance from the axis of the cylinder to that point, r, will vary from 0 to the radius of the cylinder A. Now, for any point which lies outside the cylinder, which we have called segment 2, the distance from the axis of the cylinder to that point, r, will be greater than or equal to the radius of the cylinder A. Okay, so now let us first consider a situation where the point lies inside the cylinder. For convenience, let us draw the cylinder here once again. Okay, so here's the radius A. This is the axis of the cylinder. And we are considering the segment inside the cylinder, which we denote by 1. Now we know that Gauss's law tells us that the electric flux through a closed surface is equal to the charge enclosed by that closed surface divided by epsilon naught. So let's apply this law for a point which lies inside this cylinder. Let's say this is the point and the distance from this point to the axis of the cylinder is r. Now let us consider a cylindrical closed surface here like this, whose radius is r. And the shaded region here is solid and contains charge. Let's take length of the cylinder to be L. Now the electric field through this enclosed cylindrical surface will be like this. So the electric flux through this closed cylindrical surface will be equal to the electric field, which we'll call E1 times the area of the closed cylindrical surface 2 pi RL, is equal to the total charge enclosed in this volume, which we can write as rho times the volume of the enclosed cylinder pi r square L, and the whole thing is divided by epsilon naught. So let's find E1 from here. We see that pi and pi cancels out, L and L cancels out, and R on the left hand side cancels out one of the R on the right hand side. Okay, so we can write down E1 as rho times R divided by 2 epsilon naught. And this is the magnitude of the electric field at any point inside the cylinder. And what about the direction? Well, it acts along the vector r. So for the electric field vector, we have to include a unit vector r here. Okay, so now let's turn to the second case where the point lies outside the cylinder. For convenience, let us again draw a cylinder here, and this is the axis of the cylinder. Now let us take a random point outside this cylinder, let's say this point, and denote the distance of it from the axis with r, and then draw a cylindrical surface with radius r like this. Let's say the length of the enclosed surface is L. The electric field through this closed surface looks like this. So now let's apply Gauss's law for this closed surface. And what does Gauss's law say? Well, the electric flux phi through a closed surface is equal to the total charge enclosed into the closed surface divided by epsilon naught. Okay, so what is the flux through this closed surface? Well, it is the electric field here, which we denote by E2, times the area of the curved surface, which is 2 pi RL. And what is the enclosed charge? Well, here the enclosed charge is the charge of this shaded region of the cylinder, which is charge density rho times the volume of the shaded region by a square L, and the whole thing is divided by epsilon naught. So now we can find out the electric field from this equation. Here we can see that pi and pi cancels out, L and L cancels out. So we have rho times a squared divided by 2 epsilon naught r. Now this is the magnitude of the electric field. To write it as a vector, we have to include a unit vector r hat in this equation. So finally, we see that we have two separate equations for electric field for these two regions. The first equation is valid for r less than equal a, and the second equation is valid for r greater than equal a. Now you can see that both the equations should be valid for r equal a, and if you put r equal a in both the equations, you'll see you get the same result. Now let us check how the electric fields in these two regions vary with distance r. So in region 1, the electric field, you can see, is proportional to the distance r, where r is less than or equal to a. Now in region 2, as you can see, the electric field is inversely proportional to the distance r, where r is greater than or equal a.